Imagine you're building an AI that reads tweets. Here's what it sees. OMG. Best coffee ever hot beverage. Smiling face with heart eyes at cafe life. Hashtag Monday motivation. To you, this is simple. To a computer, it's chaos. Where does one word end and another begin? Is coffee the same as coffees or coffee with a capital C? What about the emoji? The hashtag? The mention? Before any machine learning can happen, raw text needs to be transformed into something structured, clean, and analyzable. This is text preprocessing, the unglamorous but absolutely critical first step in every NLP pipeline. Welcome to Text Processing Fundamentals, where we turn messy human language into data machines can actually work with. Let's start with the foundation, tokenization, splitting text into individual pieces called tokens. Sounds simple, right? Just split on spaces. But watch what happens. Don't worry, we'll handle it. If we split on spaces, we get don't as one token. But that's actually two words. Do and not. The apostrophe contracts them. And what about New York City? 3 words, but one entity, one semantic unit. There are 2 main types. Word tokenization, breaking sentences into words. I love NLP becomes I love NLP. Sentence tokenization, breaking paragraphs into sentences. DR. Smith arrived. He was late. Is DR the end of a sentence? No, that's an abbreviation. Modern tokenizers are smart. They handle contractions. Can't becomes can and not punctuation. Hello becomes hello and exclamation point. Special cases. URLs, emails, numbers with commas. Libraries like NLTK, spaCy, and the hugging face tokenizer do the heavy lifting. But understanding what they're doing under the hood, that's what separates beginner from expert. Next challenge, variations of the same word. Run, runs, running. Ran. To a human, these are clearly related. To a computer, for completely different strings. Enter stemming and lemmatization, 2 approaches to reducing words to their root form. Stemming is crude but fast. It chops off prefixes and suffixes using rules. Running becomes run. That works. Flies becomes FLI. Wait, what? The most common algorithm, Porter-Stemmer, uses brute force chopping. Fast, but you get nonsense stems like universe from university. Lemmatization is smarter. It uses vocabulary and grammar to find the true root, the lemma. Better becomes good. It knows it's an irregular comparative ran becomes run. Handles irregular verbs geese becomes goose. Understands plural forms. The trade-off? Lemmatization is slower because it needs to check dictionaries and understand part of speech. When to use which search engines. Stemming. Speed matters and FLI will still match flies. Sentiment analysis? Lemmatization. You need actual words for accuracy. Here's the kicker. Modern transformers like BERT don't use either. They use subword tokenization, breaking words into smaller pieces. Unbelievable becomes believe, able. Best of both worlds. Now that we have clean tokens, what are they? Nouns, verbs, adjectives, Part OF speech tagging, or POS tagging, labels each word with its grammatical role. Take the sentence. They can fish. They, pronoun can. Wait, is it a verb meaning are able to, or a noun meaning a container? Fish, verb or noun. Context determines meaning. In they can fish. If can is a verb, then fish is also a verb. If can is a noun, then fish is a noun too. POS taggers use the Penn Treebank tag set, about 36 tags. NN, noun, singular VBZ, verb, third person singular present JJ, adjective RB, adverb. Why does this matter for NLP? First, disambiguation. Book as a noun versus verb. I read a book versus I book a flight. Second, information extraction. Finding entities. Nouns and proper nouns are your targets. Third, feature engineering. Count adjectives for sentiment analysis. More adjectives often mean stronger opinion. Modern POS taggers use machine learning. They look at the word itself, surrounding words, the context, window, common patterns. spaCy's POS tagger is 97% accurate, better than many humans. It's trained on millions of hand-labeled sentences. Here's the output. The quick brown fox jumps, the determiner. Quick adjective. Brown adjective. Fox noun. Jumps verb. Each word tagged and ready for deeper analysis. Individual words are nice, but language works in phrases. That's where chunking comes in. Chunking groups tokens into meaningful phrases, like noun phrases or verb phrases. Take. The big red car crashed into the sturdy brick wall. Without chunking, you have 10 individual words. With chunking. The big red car. Noun phrase, one entity crashed into. Verb phrase, one action, the sturdy brick wall. Noun phrase, one object. This is called shallow parsing. Unlike full parsing, it doesn't build a complete tree. It just finds the major chunks. Common chunk types: NP noun phrase, the tall building. Artificial intelligence VP verb phrase, is running quickly. Will have been completed PP, prepositional phrase. In the morning, under the bridge. Why chunk? First, entity recognition, multi-word entities. New York City, machine learning. Second, simplified analysis. Instead of analyzing 10 words, analyze 3 phrases. Third, pattern matching. Find structures like NP plus VP plus NP4 subject verb object. Chunking uses regex-like patterns over POS tags. Determiner plus 0 or more adjectives plus noun equals noun phrase. It's the bridge between word level and sentence level understanding. Chunking tells us which words go together. Dependency parsing tells us how they relate. Every sentence has a root, the main verb. Every other word depends on something. Look at. The cat sat on the mat. Sat is the root, the main action. Cat depends on sat. Who sat? The depends on cat. Which cat? On depends on sat. Where? Mat depends on. On what? The depends on mat. Which mat? This creates a dependency tree, a directed graph showing how every word connects. Dependency types of labels and nominal subject. Cat is the subject of sat determiner. The determines cat preposition. On is a preposition object of preposition. Mat is the object of on. Why is this powerful? First, question answering. Who sat? Follow then link to cat. Second, information extraction. Find agent action patient relationships. Third, translation. Different languages have different word orders, but dependencies often transfer. Fourth, semantic understanding. John gave Mary a book. Who's giving? Who's receiving? What? Modern parsers like spaCy use neural networks trained on annotated corpora. They predict both the dependency head. Which word does this attach to? And the dependency label. What's the relationship? The output is a parse tree you can traverse programmatically. It's structured, queryable syntax. Let's put it all together. Here's the text processing pipeline in action. Raw text. The runner's shoes were amazing. She ran 5K in 20 minutes. Step 1, tokenization. The runner's shoes were amazing. She ran 5K in 20 minutes. Step 2, lemmatization. The runner B shoe be amazing. She run 5K in 20 min. Step 3, POS tagging. Determiner noun verb, adjective punctuation, pronoun verb, number, noun, preposition, number, noun, punctuation. Step 4, chunking. Noun phrase, the runner's shoes. Verb phrase, were amazing. Noun phrase, she. Verb phrase, ran. Noun phrase, 5K. Prepositional phrase, in 20 minutes. Step 5, dependency parsing. Complete syntactic tree showing all relationships. From one messy sentence to a rich, structured representation ready for machine learning. In the next video, we'll see how traditional language models use these tokens to predict text. But for now, remember, every chatbot, every translator, every voice assistant starts here, with the unglamorous but essential work of text preprocessing. You've just learned the fundamental techniques that power 90% of NLP systems. Practice them. Master them. They're the foundation everything else builds on.